There is something okay, start recording. Okay, I'm sharing my screen. So I'm just gonna stop. Let me see. Stop sharing for now. Okay, I already done that. All right, so I hope now I'm gonna share the screen. Can you see my screen now?
Yes.
Okay, so we're gonna start with question 6, then we're gonna go backwards. So there's something that I just want to tackle per question. So in this question 6, it says let f of x, which is equals to x cubic plus 2 into comma, x is an element of 0 to 1. Let P be the partition of 0 to 1, given that P equals to 0 into 1 over n, 2 over n dot dot, n minus 1 over n and 1. So this is a partition. So this one, normally what is happening here, you used to work an integral, or you used to work with a Riemann sum, whereby the partition, we're gonna divide it into equal terms. So when you divide it into equal terms, then you're going to find the upper and the lower for that. So, but this question is not the same. Then the question here, what we are asked to do, it says, show that the upper and the lower sums converge to the same limit. So which means we are going to show that exactly this function that we are given, it converges to the same limit. We are given a hint. This hint is just showing us that the sum of k when equals to 1 into n of k to the power cubic equals to n squared in brackets n plus 1 to the power 2 divided by 4. So this is just the hint that we can use, but here the point is that we are given, we have to show that the upper and the lower sums converges to the same limit. So now in this question, you might ask yourself, what is the upper and the lower sums? So the upper and the lower sums, I'm going to give you all the necessary definitions that you're going to need now in order for you to answer any question related to this. So now if we have this equation, the first thing that I'm going to write in our question that we are given that f of x equals to x cubic plus 2. So you are also given a hint, but I'm going to come back to a hint later. So when we are given f of x equals to 2, we are also given that the partition, which we call it P, which is equals to, is going to start at 0, then it goes to 1 over n. Then after 1 over n, it goes to 2 over n. After 2 over n, then it will go to n minus 1 over n. Then after that, the last one is 1. So this is our partition. So now the first thing that we have to talk, what is the upper sum? What is the upper sum? So while I'm giving you the definition, I will be answering this question. So the upper sum, which we can denote it as U means upper, of f. The f is a function, f and p. F is of this function, and the partition, which is p, f and p, is defined as is the sum of the areas is the sum of the areas of the rectangle you can delete that L there. This A is a rectangle determines determined by the function value values at the upper endpoint. At the upper endpoints of each subinterval intervals. The subintervals are the points like the one when we talk about the subintervals. Subinterval, we divide our partition to be, it start at 0, it's going to be 0 into 1 over n. This is a subinterval. Then we're going to have 1 over n into 1 over 2, 1 or 2 over n. Then after that, we will have n minus 1 over n into 1. These are the subintervals. So the subintervals which we started here, it started at 0 and it ended at 1. So our u of p, which is u, then our u of f and p is the same as equals to 1 over n multiplied by the function where there is, we start for the upper, we are going to start, we don't start at 0. We're going to start in our interval, in our partition. We start in the right side, which we're going to start at 1 over n. So when we start at 1 over n, our f of n is going to be 1 over n plus f of 2 over n plus f of n minus 1 over n plus f of 1, which we can just put the close brackets. So this is the upper interval. This is the upper one that I showed you. So the lower sum. So lower sum, I won't write it. I'm just going to read it because it's the same. It read as follows. It denotes L of, this is denoted as L. We can write it as L of P, F of P. So is defined as the sum of the area of the rectangles determined by the function values at the lower endpoints. Each subinterval, in this case, the subintervals is the same as 0 to 1 over n, the way I've written it at first. But our L over n, our L over f of p is going to be equals to 1 over n, whereby we start at f of 0 in the left side, then plus is going to go to f of 1 over n plus f of 2 over n plus f of n minus 1 over n. So what you must take into account is that in the first upper, we started at 1 over n and it ended at f of 1. But in the lower one, we started at f of 0, then it ended at n minus 1 over n. So now when you have this, we can now simplify this into our equations. So if I start with u of f and p, you will see that we're going to have 1 over n in such a way that our u of f and p is going to be, we substitute in the equation, which is x cubic plus 2. We're going to have 1 over n cubic plus 2 plus, you can even brackets if you want to brackets so that you don't make mistakes, plus 2 over n cubic plus 2 plus again n minus 1 over 2 over n cubic plus 2, which you can brackets, then plus 1 cubic plus 2. So if you simplify this, you will see that your equation here, you will have 1 over n in brackets 1 over n cubic plus 2 plus, again, you're going to have n2 over n cubic plus 2 plus. So everywhere you will see that you're going to have a 2 inside here. But if we do the last one here, we're going to have n minus 1 over n cubic plus 2 plus, again, this one you're going to see that is giving us 3. So if we write the L of F and P, still is going to be 1 over n, where our f of 0 is going to be 0 cubic plus 2, which is going to be 2 plus 1 over n cubic plus 2 plus, again, you can say 2 over n cubic plus 2 plus again, which is going to be n minus 1 cubic over n plus 2. So when we have written this, you will see that in this limit of ours, if we find a limit, when n approaches infinity of u of f l fp, if we put here, we know that our fp in such a way that I won't really write it now, is the whole equation. We know that the limit when n approaches infinity of 1 over n equals to 0. So when we know that, we can check what will happen in this equation here if we put our limit equals to 0, our f of n. So we will see that according to this definition here, everything, if you make it to be equals to 0, all the functions here, they are going to be equals 0 equals to 0. But the limit that you're going to be left with, you're going to be left with the limit when n equals to 3, which you're going to get 3. And if you also check in this equation, limit when n approaches infinity of L of f of p, you are still going to get the same thing. If it's earlier, you are still going to get 3. So if we substitute everything here according to this equation, you will find out that your answer, you are going to have 3. So I'm still going to prove it to you how this limit. So the moment when you get 3, based on what we did here, now you can deduce that the limit when n approaches u of L, limit when n approaches u of f and p is equals to the limit when n approaches infinity of L of f of p, which is equals to 3. So therefore, it means that when n approaches infinity, both the limit there converges to 0. So it's the same limit. So by just doing this proof here, what I've written, you have just proved that these two, the upper and the lower sum, they approach to the same limit. Based as the question as that, show that the upper and the lower sum converge to the same limit. So now, because you have a hint, we have a hint, and the hint it says n to the power k, when k start at 1, k equals to 3, is that. So, but now when you have this hint here, what will happen is that we have a function. The function that we have this function. So in this function, we have x cubic. So if we can say n equals to k, which is equals to 1 of k cubic plus 2. So you will see that this is going to be n sum of k equals to 1 of k cubic plus 2 sum of n k equals to 1 of that. You can just write it like that. So now we know that when you have this, we are going to substitute this equation. When we substitute this equation, it's going to end up equals to k n squared in brackets n plus 1 to the power 2 over 4 plus the n we can just write as 2. So if we take the upper limit, for the lower limit, L, I'll just use SL. L, you know that it starts at the left-hand side. So to the lower limit, if we put here 0, if you put 0, you put 0, we are going to get, if you put, let's start with 1. If you put 1, going to be 1 in brackets 1 plus 1 to the power 2 over 4. So which this one here, when you put 1 there, is going to give you equals to 4 over 4. Remember there is plus 2, which is this one, 4 over 4 plus what? Plus 2, which in other ways, okay, let me just redo it properly. I'm just gonna do it in the board so that you can follow properly. So if we have a function whereby we can write it, we have already written it as n sum of k, which is equals to 1 of n brackets n plus 1 over 4 squared plus 2. So now what I'm going to say, when we find a limit, when n approaches infinity of L, of F and P, this is going to be equals to the limit when n approaches infinity of n in brackets n plus 1 squared over 4 plus 2. So in this limit here, we are given that our k is equals to 1. So because of we are given that our k equals to 1, instead of this limit here to be infinite, we can use n equals to 1, n equals to 1. Then you will see that our limit here is going to be 1 in brackets 1 plus 2 plus 1 to the power 2 over 4 plus 2, which is going to be equals to 2, which is 2 squared over 4 plus 2, which is going to be equals to 3. So now we have gotten L, when L is 3, we have gotten that L equals to 3. Then, if you have checked before, in our partition, we started with L with K with P, whereby P it was 1, it was 0, f of 0, it was f of 0, but it ended at f of n minus 1, f of 1. Then even the same one when we apply for the L of P, using that method where K is given, you are still going to use the same method and still your n is going to be 1, whereby your L of U of f of P is going to be 3, which is still going to be equals to, which I cannot just write now, n when equals to 1 of what? Of U of f P. So based on that, we can conclude that that limit is, you have shown that the upper and the lower sum, they converges to the same limits. So do you have any questions?
No.
Okay, so that's how you normally do it. So in each and every question, if you are not given a hint, use the first method that I showed you so that you can get to the right answer. But if you are given a hint, you can just go straight to the hint if you can work it out. But if you are given a hint and you cannot use it, use your own ways that you normally use before, which you can think you can get the better answer. So now we're gonna go to question 5. So in question 5 here, it says consider the function whereby you are given f of x equals to ln of 2 plus x. Determine the Taylor polynomial of degree of n for f at -1. Write the answer in sigma notation. So we are going to write our answer in sigma notation. So what is the meaning of that? The first thing that we have to take into account is the Taylor polynomial of degree. So which means we must know the formula of Taylor. So the formula of Taylor, I'm going to give you the one for the ln. For ln, remember in this function, is logarithm. It's logarithm. So when the ln is logarithm, then in order for me to get the answer for that question, I'm going to give you first the general form. General form of logarithm or of linear using for Taylor series expansion. So we have a standard one for ln, which is ln of x plus 1. So ln of x plus 1 can be when x, remember when x equals to 0. In that question that we were doing, we are given when x equals to -1. When x equals to -1, I mean, you can see it's written -1 at of f at -1. So now what we're going to do here, our ln of x plus 1, it can be expanded as ln of x plus 1. It can be expanded as equals to x minus x squared over 2 plus x cubic over 3 minus x to the power 4 over 4. Then I'm just going to say plus dot plus. Then we're going to have -1 to the power n plus 1 into x to the power n over n plus it's still going to be continuing. So now, because our function that we are given, the function that we are working with, it stays f of x equals to ln of 2 plus x. F of x, our f of x equals to ln of 2 plus x. So here we have to come with a way in such a way that we can deduce this to in the form of this so that we can use it. So in order for me to do that, and remember is when our x equals to 1. Our x is equals to 1. We can take this one, -1. We can take this one the other side. It's going to be x plus 1, which is, it can come to this one here, which is equals to 0. So now we can let our y equals to x plus 1. So if we let our y equals to x plus 1, then it means that we can come to our ln of 2 of x, 2 plus x. Our ln of 2 plus x, we can change this to be y minus 1, which is equals to x. So where there is x, we're going to write y minus 1. Then this equation is going to come as ln of 2 plus, in brackets, y minus x minus 1. So if we check now, you will see that we can write this equation as ln of 2 minus 1. We're going to have 1, which you can write it as y plus 1. And now it's in the same form as this one. So now what we can do, when it's in the same form of this one, we can now write it as y. The way here we write is going to start as y minus y over 2, y squared over 2 plus y cubic over 2 over 3, and then minus y to the power 4 over 4 plus, and which means it can be negative 1 to the power n dot y to the power n over n, plus again like that. So now we have written this in that form of Taylor, but now the question stated that we have to, it stated that determine the Taylor's polynomial of degree n, which we have just did it. For f at negative 1, we just did that. Write the answer in sigma notation. So we haven't answered this question which state that we have to write it in sigma notation. So which means now we have to convert what we have there in sigma notation. So when we convert what we have in sigma notation, we have already showed that the last term that we have is negative 1 to the power n dot y to the power n over n. So in other words, we can write our function as f of x, which it can be equals to sigma when negative 1 to the power n, which is n plus, here is n plus 1, which is n plus 1 into y to the power n over n, whereby our, or you can use, instead, because we are using n here, we can use the value k. Let's use k. So if we use k, it's going to be k plus 1 into k over k. So whereby our k equals to what? Equals to 1 into n. So now we have this. So it means that our function, remember, our function is in terms of y, and our y equals to x plus 1. So where there is y, we are going to substitute with x plus 1. Then our f of x is going to be equals to sum of negative 1 to the power k plus 1 into x, where there is y, we substitute with x plus 1. The equation, we are returning back, we are substituting back. It's a back substitution over, where there is k, we write k to the power k into our k equals to 1 into n. So just by doing this, we just did what? We just answered that question, which state that did have write the answer in sigma notation. So everything that we did there is 5 marks. So the reason part, if you check in your, if you Google it, you say Taylor polynomial of degree n, you will get the standard format of the standard n. You will get a standard Taylor So you will get a formula. So the formula for Taylor, it will show you that the Taylor polynomial of degree n f of f at x equals to c equals to Pn of x f of c plus f prime of c x minus like that. Maybe I don't know how to open this, maybe so that we can just view it properly. I just wanted you to see the formula only, but I'm not sure if the formula is written in terms of your, yeah, this is the Taylor polynomial of degree n of x of t. This is the formula that you follow. So you will see that is f prime, you differentiate x minus c. What is c? C is the one, the constant, the negative one. Even in the same one, you just use exactly this formula the way it is there. Then the even pride, even if you use the same one, you will see that you're going to get exactly the same thing that we have been doing until the end. So it's still the same thing. So the approach that you use, it can be more different, but it's still going to be the same. So do you have any question?
No.
Okay. So we can move. You can try also to copy this formula or take the picture, because we're gonna have a video. Then you try to follow it using each and every step. You will see that you are going to get exactly the way we did it now. So let's say, for example, now the other question state that show that for all x such that x is greater than or equals to 0 and x is less than 1, limit when n approaches r of n into -1 of f of x equals to 0. So now in this one here, when you show, you have to know what is the r of n and the -1. So do you know what is r?
No.
Okay, the r there of n into -1 is talking about the Riemann sum. So the Riemann sum, normally in this format, when they write it like this, they mean a partition. It's like you are going to start from n going to -1. So you are going to write a partition. You have to like partition it, f of x to be equals to, then this limit is going to be equals to 0. So now when you have this one here, when you have this question, this f of x, we already have an f of x, whereby now if we put between n to -1, let me Hey, why you timile so fast? And it's at 0, yo. I don't understand why is it happening.